So good afternoon, everybody. My name is Andrea Balduzzi, and I'm professor at the Friedrich Schiller University in Jena, in Germany. And I'm very pleasant to give you today a presentation about, in the frame of the project StoRIES, about supercapacitors. And what we will try to do today is to discuss about the state of the art of this technology, about the application, the current and the future, and also about the future perspective that this technology has. To begin, I would like to start with some general consideration which have to do with the energy problem. So we all know that when we are now thinking about the energy, it is obviously a problem in our society, and we need to try to go for the use of natural sources. We need to produce energy in a safe and efficient way, and of course, what we need to do is to store energy. And I think that we are all aware of the fact that the storage of energy is important, and we are kind of bombarded by the idea that we need to store a lot of energy, a large amount of energy, which of course is true, it is important, but what sometimes is not probably highlight enough is that it's not just a matter of storage, store a high amount of energy, but what is very important is to deliver and to store energy in a desired time frame. So what is really a key for the future of our society will be the realization of an effective delivery, for example, because this is necessary for an effective storage. And in our life, we have many different situations, and each of them are requiring different amount of energy and also different delivery time. And there are a large number of situations in which what we need is a fast delivery uptake of energy. And when I'm talking about fast, I'm talking about minutes or even seconds, and long repeated delivery in the order of tens of thousands or even millions of times. And when we are talking about this situation, so when we need fast delivery uptake and a long cycle life, we are talking about the so-called high-power applications. These high-power applications are many, and they are touching us every day. So, for example, at home, if you want to drill a hole in the wall, we need a driller, and these require a lot of energy in short time, so a lot of power. This, of course, can be extended when we are thinking about mining. So in this case, we have huge machinery like the one that we are seeing here that are needed to, for example, mine something. In the phone, for flashing camera, we need to take a picture, and our mobile need a power for making to have the flash. There are a large number of applications, for example, also in the automotive sector. So the stop and go function, we are going with the car in a town, there is a traffic light. When the traffic light is red, the car switch off. When the traffic light is green, the car needed to switch on again to start. And of course, we don't want to spend hours to switch on the car. This must be very fast and do many times. Or, for example, we need a lot of power in a port. When, for example, like in this picture, we have a port crane, we have a number of thousands and thousands of containers that are arriving in big port over all the world, and every day, thousands and thousands of these containers are brought from the ferries to the ship to the port and back. And these actually are a typical high-power application, because what we need is to have a lot of energy to, for example, lift this container. Then we need to shift this container for a certain distance, which will never be kilometer. So we don't need a long energy to cover this distance. And then we will lift the container on the port, for example. In this case, if you are able to recover energy, we could recover the energy we were spending before to lift it. So these are classical examples of high-power application. There are also examples that are maybe less obvious, but they are very relevant. One is the grid. There are fluctuations of grid in our grid, and sometimes we need to buffer this fluctuation extremely fast. And we need to have devices that can deliver energy or can uptake energy fast enough to compensate the changes in the time frame that we want. Or, for example, what we can also have is the possibility to use a power system also for bus in town, where we are thinking about a typical trip of a bus. What is happening is that a city bus is never making long distances between one stop and the other. And in every stop is typically staying for 1 or 2 minutes, depending on which time of the day we are. And in this time, it will be is it possible if there are energy storage system able to do this, to charge this bus and to give to the bus enough energy to reach, for example, next stop, where in the time which the people will go out in, it could be recharged. So these are just few examples of what we are considering high power application. And basically, today we were talking about the devices that are used nowadays to fulfill this application. And these devices, and especially we will focus on the supercapacitors. Before to do this, before to go in depth on the properties, on the mechanism, on the state of the art of the supercapacitors, I think nevertheless that will be that is interesting to compare initially the supercapacitors with the battery, and especially with the lithium-ion battery, because these two devices, supercapacitors and lithium-ion battery, are in fact the two devices that are used to fulfill all the high-power application that we were describing 1 minute ago. And these high-power devices are devices that are commercially available and are used in a large number of different types of applications. Before to compare, I would like to make a point about the names. So let's say lithium-ion battery is a quite clear name, is defining a certain device. Supercapacitors, in contrast, is a little bit less precise, because with supercapacitors, actually, we are indicating a large number of different types of devices. And one can find many different synonyms of this word. So, for example, sometimes supercapacitors are called ultracapacitors. In other occasions, are called electrical capacitors, or they can be called even electrical double layer capacitors, EDLCs. In this presentation, we will mainly use the word supercapacitors or electrical double layer capacitors, but nevertheless, it's important to know that it's possible to meet also to find also different type of names for this type of devices. What we are seeing now in this graph is a comparison of the two devices that we were discussing, that I was mentioning before, so the supercapacitors and the lithium-ion battery. And what you see here is what we are normally, what is called as a Aragon plot. Aragon plot is a plot in which it's possible to compare the specific energy with the specific power of a certain device. And because in this graph, the specific energy is expressed in watt-hour per kilo, it's possible then, dividing the energy for the power, to get indication also on the time frame in which these devices can be used. And what we can see immediately from this picture is that supercapacitors are devices that display extremely high power, so a power which is higher than the one of the battery. On the other hand, the energy of this system is lower than the one of the battery. This difference, so the different energy and power of supercapacitors and lithium-ion battery, is due to the fact that this system are relying in two different storage processes. In the case of the lithium-ion battery, as probably is well known for all the attendees, we are talking about a chemical storage, because basically what we are having is a charge transfer. The lithium-ion is moving through the two electrodes during the charge and the discharge process. In the supercapacitors, what we are having is typically a physical storage. That means we don't have chemical reaction, we don't have charge transfer, but we have a rearrangement of charge. These two processes are different. On the one hand, the chemical process allow us to store more energy, and this is the reason why lithium-ion battery has higher energy. But on the other hand, the physical storage allow us a fastest process, and this is the reason why this system has a higher power. What this different storage mechanism is also affecting is the time of charge and discharge. When we are talking about battery, we are typically talking about minutes or hours. While we are talking about a supercapacitor, we are more on the range of seconds or minutes. This system display also a different efficiency due to their different storage mechanisms. Lithium-ion batteries are extremely efficient. They have a cycle efficiency higher than 90%, but supercapacitors are even higher, are more than 95%. And this difference actually is impacting very much the cycle life of this system, because battery is always difficult to give a precise number, but let's say high power lithium-ion battery may stand for several thousand cycles, depending on the rate we apply. When we are talking about supercapacitors, we are talking about a device that have a cycle life in the order of 500,000 or even 1 million of cycles, so extremely high cycle life. As we mentioned before, the energy of the lithium-ion battery is significantly higher than the one of the supercapacitor. We are talking about one order of magnitude of energy in terms of differences. On the other hand, the power of supercapacitors is more or less one order of magnitude higher than the one of some lithium-ion battery. So what we have is really a difference in terms of main properties for these two devices. Supercapacitors are high power system which has a very high cycle life which is much higher than the one of the lithium-ion battery. What I would like to show now to you is, I think, an interesting comparison about the use of lithium-ion battery and supercapacitor in high-power application. I think that this comparison that came out actually of a work that John Miller, that was one of the most known scientists, unfortunately he passed away this year, was basically presenting already many years ago in 2008 together with Andrew Berg. But I still think that this comparison is still actual, because it's a very nice example of let's say how these two systems can be used in a power application, and what are the advantages and disadvantages associated to their use. And specifically, what in this slide we will see is the use of supercapacitors and lithium-ion battery in a city bus with a stop-and-go driving. So basically, in these buses, which, I mean, there are thousands and thousands in all the world, what they're doing is that they're doing thousands of start and stop during a day. They go from one stop to the other, the people are going out. And what is required, of course, for this system, if you wanted to implement a storage system, is a high cycle life. And then what is extremely important is that we need to dissipate the heat generation, which is due to the charge and discharge losses. And so in this study, Miller and Bork were comparing two systems of supercapacitors, which was having 3,000 farad. That is an important point. When we are talking about supercapacitor, normally we are presenting the data in farad with an operative voltage of 2.7 volt against an high power battery, which had 12 ampere hour of capacity. And basically, what they have been done during this to realize this comparison was to perform tests in which they were measuring the amount of energy that was captured by each device for various constant current charge time. And the stored regenerative energy was the amount of energy that could be discharged after the charge. So basically, the goal was to understand what you can really give after you charge the system after you use. And they were, as I said, using a supercapacitor working at 2.7 volt. The battery had a potential cell voltage of 2.8 during the charging. The initial state of the supercapacitors was 1.35 volt, and the battery was 10% of state of charge. And what you can see here is actually the result of this comparison. And what you see is a graph in which we have the charging time, so that's going in seconds, and the specific energy. And this graph is quite interesting because it's showing us immediately the differences between these two devices. Because what we can see is that if you are considering a lithium-ion battery, and you are now considering a time frame that is larger than 10 minutes, you see that actually there is no comparison, because the battery displays much higher energy than the one of the supercapacitor. So it doesn't make any sense to use a supercapacitors if you wanted to go in the range of 10 minutes. his energy is too low, simply. When you are then reducing the time to 100 seconds, there is still a considerable difference, but still the gap become much lower. It's not anymore 15 times, but it's 5 times. When then you move to 10 seconds, here it becomes very interesting, this comparison, because what you can see is that basically the capture energy of supercap and battery is basically the same, is where they are crossing. But what is the big difference is that supercapacitor can discharge more or less 95% of this amount. So the two lines, the two blue lines are very close to each other, while the battery can only discharge 50%. So what is the message of this figure? That when you are now in the time frame of 10 seconds, the supercapacitors is working a much more effective way than a lithium-ion battery, for example. And then if you are even decreasing the time and you go to less than 10 seconds, well, we are reversing the beginning. So in this case, makes much more sense to use a supercapacitor than the lithium-ion battery, because in fact, the energy that you can utilize and in a proper way is much higher than the one that you can use in a lithium-ion battery. So taking into account this point, what we can say is that lithium-ion battery, are in fact not well suited for very fast application. Why? Because they have enough energy to fulfill the need. That is not a problem, because they are order of magnitude of energy higher than the supercapacitor, but they are working inefficiently. So we are not utilizing them in a very effective way. And the supercapacitor, on the other hand, are much more appropriate for this time frame because they are much more effective. Now, this is an important point, because in our daily life, many applications are actually fulfilled by lithium-ion battery rather than supercapacitor. And we will see that this is one of the big challenges of the supercapacitor technology, to try to increment the market due to the possibility to have a more efficient system than the one that are currently possible, because they are used by lithium-ion battery. And so what I would like now to show is the state-of-the-art and the future application of this technology, so of the lithium-ion battery, of the supercapacitor, sorry. And what you're seeing here is a scheme of classical supercapacitors with some detail about the content of this system. So as you see, the supercapacitors are in fact very similar in terms of format to the lithium-ion battery. So you can find them in a prismatic form, in pouch cell form. So in that sense, they are very close technologies, lithium-ion battery and supercapacitors. Like in a prismatic battery, also here you have a layered, let's say, structure in which you have a positive pole, in which you have a aluminum current collector where you have coated the positive electrode. Then you have a separator, which then is impregnated with an electrolyte, and then this separator is dividing the positive with the negative electrode, which is again an electrode of carbon, in which we are basically coated on aluminum current collector. The material, and then we will see in detail later, used for the electrode as active material, we are using activated carbon, as a conductive agent carbon black, and as a binder PTFE, PVDF, or CMC. So the conductive agent and the binder are basically analogous to the one that we are using in many lithium-ion battery. The active material is then a carbon, but not a graphite, but an activated carbon, which is a porous carbon, which we will discuss later on. As electrolyte, what is used are solution of organic solvent, typical acetonitrile. Propylene carbonate was used in Japan because acetonitrile was banned in this country for many years, but right now most of the system are working acetonitrile. And basically, then we are dissolving in this solvent a salt, typically is an ammonium-based salt, like this tetraethyl ammonium tetraforborate, in a concentration of more or less 1 mole, 1.2 mole maximum. And the combination of electrode and electrolyte allowed the realization of systems that have a set voltage of 2.83 volt. There are produced overall the world of supercapacitors. So these are commercial available systems. In US, there was Maxwell that has been then sold to Tesla. As far as I know now, that they were probably going back again or being an independent companies, but I'm not 100% sure of this. There are companies in Asia like GSR Micro, in Australia, Cap XX. And then in Europe, we have a company like, for example, Skeleton, which is an Estonian-German company, which is working on the production of and development of supercapacitors, electrical double layer capacitors. The market of supercapacitors is a market which is significantly smaller than the one of lithium-ion battery, but is existing. So this is not something that is not a reality. So the market of supercapacitor is a reality. We are talking about, you can see here, let's say, indication, you can get an indication about the market in millions of euro. This market is a constant increase. So in the last 20 years was constantly increasing and is foreseen it will keep growing. And the market can be divided in two main parts. One are the small scale ADLC, which are mainly used for electronics, some of the properties of the application we were discussing before. And then we have the large scale ADLC, which are ADLCs that have capacitance larger than 100 farad, which are mainly used for electrical engineering. And the mobile sector, so the sector in which supercapacitor will be used in automotive, bus, and transportation, is expected to grow the most. And in 2022, the market was about estimated on the order of 1.5 billion of euro. So a market which is again not as big as the one of lithium-ion battery, but relevant. So a market is existing and is growing. What are the pleasant applications of this system? So we have to consider that the device that we were discussing, you were mentioning 1 minute ago, they typically have an energy density in the order of 5 to 8 watt-hour per kilo. These systems are used, for example, in the forklift, in the crane of the port, in some storage, in some application, automotive industry. And what is important to remark here is one point, that if you are now looking the cost of the power, it's clear that to buy power from a supercapacitor is extremely convenient because it costs less than €1 per kilowatt. What is extremely inconvenient is to buy energy, because the cost of the energy for a supercapacitor is something like €4,500 per kilowatt hour, which is enormously higher compared to lithium-ion battery. This is actually one of the reasons why many companies prefer to use still batteries than supercapacitor for a power application, because basically what they are doing is that they are, let's say, preferring to have an efficient system, as we said before, which is cheaper in terms of energy than an efficient system which may not fulfill all the power. So this is actually a big challenge for the state of the art, and this challenge will also affect the future of this technology. What we are seeing here is a slide that I was receiving by my colleague Sebastian Pohlmann, which is working in skeletal technologies, and in which you can see the future applications that are foreseen for supercapacitors. So, for example, in the automotive, supercapacitors are seen as a very valuable component for example, power support solution, 48-volt active suspension for cars, for the push-to-pass application. But they're also very interesting for transportation heavy equipment, so train, mild hybrid bus, buses for the mild hybrid bus energy storage, cars for light train, rail. So there are a number of applications which are also already existing. So there are, for example, in town like Graz or some town in Portugal, Graz in Austria and some town in Portugal, where supercapacitors are, for example, utilized in train, in local train. They are seen as a very valuable or very interesting for grid applications. So, for example, wind turbine pitch control or microgrid power back and quality. And what is also a very interesting application for this system that is foreseen for the future are the industrial applications. So, for example, peak loading shaving to cover the short peak power demand, but also, for example, in storage places like the one that you see in this picture. In these storage places can be extremely big. Most of the time, you have kind of robot or machine that are moving from one place to the other to bring things, to order things. Actually, the distance that are covering are not kilometer again, like the one of the crane. So in this case, people are looking for the implementation of supercapacitor to realize systems that can have a cycle life large enough to really be utilized for a long time for this purpose of basically to move boxes or different kind of items from one place to the other in this basically large storage. But what is very important to remark is that if we want to introduce supercapacitors in this new technology, it's important that some of the feature of the state of the art will be improved. First of all, what we need to do is that the energy density of this system should be increased significantly. So from the 5 to the 8 actual watt-hour per kilo, we should try to move to 15, 20. So it's almost basically we have to double the energy density of this system. At the same time, we should keep the cost of the power as low as it is now, but we should reduce significantly the cost of the energy. So it has been estimated that in order to be really competitive, the cost of the energy for this device should be lower than 3,000 euro per kilowatt hour. So, of course, this is a challenge because what we need to do is really for this technology, what is necessary to do is really to increase significantly the energy density and reduce the cost, which represent clearly a big challenge. And while talking about cost, I think it's also interesting to get an indication about the cost of the different components for these devices. As we said, the architecture of this supercapacitor is very similar to the one of lithium-ion battery. And what you are seeing here, so we have separators, we have cell part, we have electrode, electrolyte, and what you see here on the left is actually the actual cost percentage of the component. So what you can see is that, for example, the electrolyte, which is the blue, cost more or less something like 27% is 27% of the total cost. The electrode 28%, and then there is a larger share of cost which is given by the separator, which is more or less more than 20%, and the cell part and production, which again account for more than 20%. If we are then going a bit more in detail about the electrolyte, and we can see that the cost of the electrolyte is basically divided between 60% of the conductive salt and 40% of the solvent, so the acetonitrile we were discussing before. And then in the case of the electrode, what we know is that the carbon is something like 39%, the binder account for 1%, like the conductive additive, and what it costs a lot is actually the current collector. Now, here we have to be a little bit careful because the fact that is this large share of cost is not coming by the price of the aluminium, which we know is already, for example, is much less than the one of copper, but to the fact that we have a lot of aluminium in. So here is the quantity that basically make the cost of this system. And what has been forecast and partially has been already realized is that it will be in the future possible to decrease significantly the share of the separator and the cell production, so to have something like 25% for the two of them. And that, of course, will lead to a significantly higher share of the cost for the electrolyte and for the electrode. And what will be extremely important to have is that in the future, the cost of all components should be less than 20 euro per kilogram. Now, that was an overview, let's say, about the application, about the market, component cost on supercapacitor. But of course, what it will be very interesting, what is very important to understand is how these systems are working, because if we want then to reach the goal that we were discussing a few minutes ago, it's clear that the only way that we have is really to improve the process that are taking place, the storage processes that are taking place in this system. And that can be done only knowing very well what is happening in these devices during the charge storage. And what you're seeing here is a picture of the storage mechanism that is taking place in electrochemical double layer capacitors. So these are synonym of supercapacitors. And what you see is that in this system, the charge is actually stored through the formation of a double layer between the polarized electrode and the electrolyte and the ions of the electrolyte. Basically, we are forming a double layer between the electrode and the electrolyte. Why? Because basically we have two carbon that can be polarized, and in the discharge state, when none of them is polarized, the anion of the electrolyte are, of course, dispersed on the solvent. When we are charging this electrode, what is happening is that in the electrode, which is, we see here, negatively charged, for example, the positive ion of the electrolyte are basically getting closer to this electron and form this this double layer. And the same is true in the other side. But in this case, of course, where the electrode is positively polarized, the anions, so the negative ion of the electrolyte, are basically approaching the electron and forming this double layer where we are storing the charge. So this is a pure physical process. There is no chemical reaction. Actually, this process then lead to the possibility to store energy. And what you are seeing here are two important equations. I will not go during this presentation very much on equation or expression, but I guess that this is very important. These expressions are nevertheless very important because they are giving us immediately the idea of what is important if you want to reach the goal that we were discussing before. Why? Because we see that the energy, the maximum energy of these devices can be described by this simple equation. So is equal to the half of the sum of the capacitance, which is basically farad per gram, so the capacitance of the electrode, times the square of the operative voltage. And the power is given by basically the square of the operative voltage divided the resistance of the systems. This makes immediately clear that in these devices, if we want to increase the energy, as we discussed before, we needed to increase the capacitance, and we needed to try to increase as much as possible the operative voltage, because of course, every increase of operative voltage will have a strong impact on the energy because it goes with the square of this parameter. What is very important to outline when we are talking about this system is that this process, so this physical process that we were describing before, is possible and is limited by only when the components are stable. That means if one of the components can be either the electrode or the electrolyte are not longer electrochemically stable or chemically stable, what can happen are Faradic reactions. And this Faradic reaction, of course, then will somehow affect the performance of the system. They may bring some charge into play, but certainly what they will do is that they will then basically reduce the life of these devices, because these devices are not being built to have a system which are going through chemical reaction. So one of the important points is that in this type of storage mechanism, the integrity, the stability of the two components, so the electrode and the electrolyte, is fundamental, because this double layer is possible only if two of them are stable. So only if the electrolyte and the electrode are stable. Typically, among the two of them, the electrolyte is the one that is the most unstable. So typically, the potential in which this storage process is possible is given by the electrochemical stability of the electrolyte. So in water, for example, this is more or less 1 volt. If you go to organic electrolyte, you can reach 3 volt. And this is the reason why in the commercial system, we are having system working between 2.7 and 3 volt. Going a little bit then in detail, what is important to understand is that when we are now storing the charge, we can define this parameter, which is the capacitance. And the capacitance is actually given by this expression, which is, let's say, not extremely complicated, so can be easily analyzed, where we have the dielectric constant of the vacuum and of the electrolyte, so this first part. Then we have the surface area, so the area in which this actually double layer is taking place. And then this product is divided by the thickness of the double layer. So that means how thick then will be the double layer that we are forming between the electrode and the electrolyte. Now, if we are seeing this equation, it's clear that the best way to increase the capacitance, and again, this is very important to increase the energy that we are storing, is to have a very thin thickness in terms of double layer. But what is very, very important is to try to have electrode which have a very, to realize a system which the area in which this double layer is formed is very large. And what does it mean this? It means that if we are using, for example, a flat surface, that probably is not a good choice because we are not able to maximize the area. What we try to do in this system is to basically utilize electrode which have extremely high surface area, because this high surface area give us the possibility to maximize the capacitance of the electrode and consequently to increase the energy of the supercapacitors. And which material can be used to do this? There are, of course, a number of material that can be realized in a pore that are porous, but let's say the material that is mainly used for supercapacitor are carbon-use material. Why? Because carbon material are, let's say, typically cheap. They can be very easily processed. They can have high conductivity, and they can be realized with extremely high surface area. So they can have surface areas that are higher than 2,000 or even more square meter per gram. So like if you would fold a few tennis field in a gram of material, which of course is a massive area, which is extremely well suited for this application. So we have done a lot of surface in which we can indeed form the double layer that we are looking, that we wanted to form. And there are different types of materials that are used for this. For example, activated carbon, which are the state of the art. We will discuss in a minute. But over the year, many materials have been used, of course, graphene, carbon nanotube, CDC, and many others have been proposed. Nevertheless, as we were seeing before, the state-of-the-art system rely on activated carbon. Why? Because these activated carbon, which are porous carbon, are extremely convenient to realize, and they are cheap. How they are realized? But for example, most of the commercial systems that are nowadays used are containing carbon that are realized from, for example, coconut shells. Why? Because there are ton and ton of coconut shells that are produced every year, and that basically is a perfect material sources, because these are organic material that can be barred. And this is exactly what is happened. So when we are realizing activated carbon, what typically is done is that these precursors are carbonized. And in this carbonization process, basically their porosity is increased. And what through this process is happening is that we have some chairs. So basically we have porous material which are blocked by some particle, by product. For example, can be carbonate salt or other type of salt. And so basically what is happening is that these materials are taken, are carbonized, and then are washed. Basically what people are doing is to remove the compound that are blocking the porosity in order to have an extremely porous carbon. When I'm talking about extremely porous, I'm talking about carbons which have a surface area in the order of 1,000, 2,000 square meters per gram, which can then be easily implemented in industrial application, and they are cheap. So these are nowadays the state of the art, and there are an established procedure to realize carbon, which are expressly utilized and expressly designed for application in supercapacitors. And what you are seeing here is basically how we are bringing then this material into real system. what basically is done is that, sorry, we are taking the carbon, which are black powder, basically, mixing with the other components, so with the conductive agent and the binder, and to realize a slurry. Then this slurry is coated over an aluminum foil, as we said before, and calendared. So is basically these composite electrodes are going through the typical processes that are basically applied to any kind of electrode of lithium-ion battery. So double coating, calendering, and then as you see here, they can be rolled, and then you can take this electrode, use the shape that you want, and basically realize the sandwich, so the layer structure that we were seeing before. So to have a positive electron with a negative electron, which are in this case identical. So in supercapacitor, the positive and negative electron are the same, are not like in lithium-ion battery where we have different material for positive and negative electron. We have a separator in between. We have a multi-layer, which will be rolled, like in this case. Then this roll is introduced in a cage. The electrolyte is filled in, and then the system is closed. And then once it is closed, is then prepared like any kind of cylindrical cell to be then sold, basically. And this is the way how industry is basically realizing carbon electrode and then is implementing this carbon electrode in this case, cylindrical cells. As we said, to do this, of course, we need to introduce an electrolyte. And the electrolyte, as we already mentioned before, is a key component because basically the electrolyte is determining the cell voltage. And nowadays, as electrolyte, we are using a mixture of a salt, which is typically an ammonium salt, like this tetraethyl for borate. Why this salt are used? Because their size is not too big. And what is also very important is that the mobility of the cation and the anion is rather comparable. Because, of course, this is very important because the mobility in this system should be as symmetric as possible because we don't want to have an electrode which is much slower or which is not able to store as much energy as the other because this will then make the performance of the system not as good as we wish. And then we take this salt and we dissolve this salt, as I said before, in typically 1 mole concentration in a solvent. What you're seeing here is a comparison of the property of the acetonitrile, which is the most used solvent in the state of the art, and then propylene carbonate that it has been used in some devices in the past, but is now not anymore so used like it was, for example, 10 years ago. And if we are now looking at the acetonitrile, what we are seeing is that this acetonitrile is actually have a very, very a good number of advantages. For example, the viscosity is quite low, the price is very good, the melting point is not bad. And what is the advantage of using acetonitrile is that this acetonitrile is giving us the possibility to have electrolyte, so solution, electrolytic solution, which display high conductivity, also a very low temperature. So acetonitrile system are working very well also, for example, at -20 degrees, that are cheap, and that they can be produced in large scale. And when then we are using this solvent and this salt, which is electrolyte, in combination with this system, as I mentioned before, we can then reach potential of 2.7, 2.8, very recently even 3 volt, 3 volt, which is a very high cell voltage for these systems already. Now, this is the state-of-the-art material. But of course, if you wanted to reach the goal that we were discussing before, so if you wanted to improve the energy of this system, it's clear that we needed to really try to make the material better than the state-of-the-art, because from what we have now, we basically reach almost the limit. So there is an enormous amount of work which is now done on trying to improve this. And when we are trying to do this, we have to consider different parameters. So for example, what it will be important to do in the future is to increase the volumetric capacitance, so the farad per cubic centimeter, from the lower than 50 that are nowadays up to 80. The electrode density should be increased. Nowadays, it's between 0.4, 0.7 gram per cubic centimeter and should go to more than 0.7. And then when we are talking about the electrolyte, what we should try to increase is the electrolyte stability, because what we said is that with acetonitrile, we are able to reach 3 volts. We should go higher, because we know that the energy goes with the square of the voltage. So the R is the voltage, the R will be the energy. But what we should also try to do is to increase possibly the temperature range of use of this system, because nowadays, due to the limited or the lower evaporation point of acetonitrile, this system can work up to 60 degrees. They work very well at low temperature, but at high temperature, 60 degrees, they are not extremely performing. In the future, it will be important to keep the low temperature, but to extend the upper temperature to 85 degrees C. So again, this is a extremely challenging task that has to be fulfilled, because basically is touching any component of the devices. But from the scientific point of view, this is also one of the most interesting, because of course there is plenty of possibilities to implement IDEA, to try to develop new material, and to try to bring this new material in real systems. How we can do this? So how we can realize systems that are better than the state of the art? And let's say here we can identify different type of approach. So we can say, okay, we start from the supercapacitors. And what we try to do is to improve as much as we can the behavior of the physical storage. So we maximize basically the possibility to utilize a physical process to store energy. That means we enlarge as much as we can the electrochemical stability, we maximize the capacitance. But what we could also think about to do is actually to replace part of the storage, or to replace even the totality of the storage with a chemical storage, because what we know is that the chemical storage is allowing us a much larger storage ability. Nevertheless, what we know is that this storage process is typically slower, so that may risk a replacement may lead to a strong decrease of power, or at the same time also a strong decrease of the cycle life, because we know that the chemical process are typically suffering more than the physical process when we are talking about long time scale. So the systems that are relying on physical process are typically having a significantly much higher cycle life than systems relying in chemical processes. And so there is really a plethora of different types of approaches that are used. One way is, for example, to maximize the capacitance of carbon material. This is an example of improve as much as we can the physical process, of course. For example, skeleton. This is again a slide that I received from my colleague Sebastian Pohlmann. Was proposing the use of curved graphene. These are activated carbon which have been designed in such a way that the capacitance of this system of this material is extremely high, without then having problem of implementing them in composite electrode, the one that we saw before. But in the last year, there have been a lot of work also in paradic material that could be used instead of carbon, or at least in one of the electrodes. One example of this is the manganese oxide. Manganese oxide is a very, let's say, famous material, rather cheap. John Goodenough was one of the first to propose this. And then in the last year, a lot of people were working. In this case, I would say that the work of Thierry Bruce and Daniel Belanger has been one of the most important. We're showing that this oxide is actually extremely interesting for the use in supercapacitors. The problem of this system is that they can be used typically in organic, in aqueous systems, so the operative voltage of devices containing them is not especially high, and also that the cycle life of these devices is not as high as of device containing this material, sorry, is not as high as the one that we are having with carbon. There were, some company were trying to introduce them in commercial devices, but to the best of my knowledge, there are nowadays no commercial system working with this type of material. And then, more recently, there have been an enormous increase of interest in the use of MXene as active material for supercapacitors. Here I give you an example of the scheme of the synthesis of this MXene, and you will see on the right some electrochemical pattern. If you're interested in this work, I would recommend you to follow the work of Yuri Gogotsi or other colleagues that are in the last year intensively working on the use of this MXene on the energy storage, and especially in supercapacitors. So far, MXene are working very well in water, but their performance are not as good as the one of activated carbon in organic electrolyte. Not much in terms of capacitance, but more in terms of cost, long life performance, and possibility to implement in large scale system this material. So at the moment, they are still not able to replace activated carbon. When we are talking about the electrolyte, what we can say is that before we were discussing about the future scenarios, so what we need to increase the operative voltage and the range of use. And basically, what we needed to do is to replace acetonitrile if possible, and also to have costs which are not exceeding 12 euro, for example, per kilo. So the point is that with the electrolyte that we are using nowadays, we will be not able to reach this standard, this parameter. So we needed to change. And for this reason, in the past, many people were working on alternative systems, in alternative electrolyte. And what has been, for example, proposed are different type of solvents, based in different type of nitrile rather than sulfonate or different carbonate, different type of salts. So, for example, based on pyrrolidinium or in piperidinium salts, so different type of chemistry. And also, that was a very big research field, but there are not a commercial system working with ionic liquid, which basically are molten salt, so salt which are liquid at room temperature. This system has been intensively investigated. What I would like to show to you here is what has been made so far with this alternative electrolyte, because I think it is an interesting, let's say, picture that is representative not only of the electrolyte, but also of the work in general that we do in novel material. So what you're seeing here is basically the operative voltage that can be achieved when we are using alternative salt, alternative solvent, alternative salt, or ionic liquid. And what you can see is that basically, if the black is the state of the art, so let's say that we set to 2.8 volt, when we are replacing acetonitrile with this alternative electrolyte, you see that we can indeed increase the operative voltage. So we can even go to 3.5 or higher. So one could think about, okay, if this is possible, this is great, because we know that the energy of the system goes with the square of the voltage. So now that we can increase so much the operative voltage, we will certainly increase the energy. This is true, but one has to be extremely careful in this. Because what we are now seeing in this picture is, for example, that when we are replacing this electrolyte in combination with activated carbon, and this is the picture of before, we can increase the operative voltage. And then what we can see is that when we are applying lower current, the energy that a supercapacitor can deliver, this is a lab scale system, but nevertheless are significantly higher than the one of the state of the art. But what is important to outline here is the fact that when we are using a supercapacitors, as we said before, we don't want to apply low current. That means we don't want to use this system in hours, because this is not convenient. We would use a lithium-ion battery. And then, so what we want to do is to use this system in a time frame which is minutes of seconds. And to do this, we need to apply high current. And what we can see here is that when we do so when we apply high current, we are talking about ampere per gram, for example, 1 or 10 ampere per gram, to give you an idea. Well, then at the end, what is happening is that the energy that we are getting out of system containing alternative electrolyte is not higher than the one of the state of the art. Why this is the case? because typically this solvent or this electrolyte are more viscous than the one based on acetonitrile. And this viscosity is basically limiting the mobility of the ion. And so when we apply our current and we are asking to our ion to move very fast, they are not basically able to follow this. And this is then well seen also in terms of power, because of course then what we have is that when we are replacing the electrolyte with alternative, typically what we do is that we can increase a bit the energy, but we lose in power. When we are going to high temperature, a bit less, because normally high temperature are promoting ion mobility, and so buffering system. But in general, at low temperature, the difference can be dramatic. So what I wanted to say with this is that the overall performance of ADLC containing alternative electrolyte is actually not higher than the one of the state-of-the-art. And with that, I don't want to say that we don't have to work in a novel electrolyte. What I want to say is that when we work in a novel components, electrolyte or the electrode, we really have to try to see which is the impact of this new material in a condition which are, let's say, similar to the one that the real system are then experiencing. So in the supercap, we are not interested in hour, for example, but we want to go to minute or second. And also, if then the cost of these devices, of this component, is competitive or lower, possibly with the one of the state-of-the-art. Now, what I would like to show to you in this last part are some also new strategies that have been developed in the last year to try basically to improve the performance of supercapacitors. And these strategies have to do with the hybridization of this system, which is one of the big topics of the StoRIES project. So one of the, let's say, strategies that has been recently shown to develop devices with higher energy density than the supercapacitor is the basically possibility to combine into one device electrode of supercapacitors and electrode of battery. Why that? Because basically what was the idea is to say, okay, battery are excelling are excellent for energy, supercapacitor excellent for power. Let's try to see if we can combine them into one device. So one electrode from battery and one electrode from supercapacitor. And what was the target of this? To realize system with the energy density that reached the target we discussed before, so 15 or 20 watt-hour per kilogram, or even higher. A cycle life which is higher than the lithium-ion battery, but a bit lower than the one of supercapacitor. But 100,000 cycle will be still a very, very good, let's say, range. And time of charge and discharge, which are in the order of minutes of seconds. So basically, you wanted to extend a little bit the time scale in which this high-power system can be used. So basically, this was the idea to try to realize devices that are in between, so that are covering actually this green area, which is the area of interest. Because basically what is happening right now is that the technology that will be able to cover this area will be the technology that will be basically dominating the high power application, because then it will be the technology that can be used in a time frame that is nowadays basically covered by both of them. And if we wanted to do that, so if you wanted to combine an electrode of battery with an electrode of supercapacitor, we have basically two possibilities. So one type will be to combine a cathode of lithium-ion battery with an anode of supercapacitor. That means we can take, for example, a cathode of a battery like a lithium iron phosphate or NMC, where you have already lithium inside, because the cathode is the source of lithium in lithium-ion battery. And then basically what you do is that you're using as a negative electron, not a graphite, like in lithium-ion battery, but an activated carbon. This system will be quite easy to implement. Of course, we need to work in balancing, but they already have basically everything they need. You could use an electrolyte for lithium-ion battery. The lithium is inside the cathode, and then basically you could operate them if you find a good balance. The limit of this system is that they will not have a very high operating voltage, so 3 volt. So again, this will not be very convenient, because then would probably not have give us the chance to have a very good performance. But Another possibility, which is more interesting, is actually to combine a graphite, so an anode of lithium-ion battery working a very low potential, like the one of the lithium-ion battery, with an activated carbon. Now, this combination is very interesting because we could reach devices that are above 4 volt, so a very high cell voltage. The problem in this system is that when you assemble them, what they are missing is the lithium, because basically to work, graphite need a lithium, but activated carbon don't have lithium. So basically, what you need to do is to find a way to bring these electrodes together and to bring lithium into them so that they can operate lithium ion. These systems are actually available, are called lithium-ion capacitors. There are companies like JSR Micro or Beyond that are producing them. And basically, these systems are relying in graphite and activated carbon. What they do industrially to lithiate them, this is a process which is called pre-lithiation. So we need to assemble them and then to bring in the system lithium is to use auxiliary lithium metal, so that basically you are putting, for example, a stripes or a piece of lithium behind your graphite, and then you are putting the lithium inside. Or you could use the electrolyte, or more recently, different strategies like sacrificial salt or cathode have been used. So basically, this technology is nowadays existing. Is a technology that can be both, but there is a problem related on the pre-lithiation process. So this pre-lithiation represents a technological issue because to have a large amount of metallic lithium is clearly not something that is so easy to handle. So we need a lot of precaution, a lot of conditions that make this handling safe and effective. And so this technology is nowadays facing the problem to try to see how can be this pre-lithiation process optimized. Nevertheless, are commercial. And so what you are now seeing here is a kind of revised Dragon plot. We were starting for Dragon plot where we have lithium-ion supercapacitor. Now we can add also what we can call hybrid ion capacitors, so hybrid systems, which are somehow in between the two of them. Each technology has its own advantage and disadvantage. Among the high-power systems, supercapacitors are still the largest. Metal-ion capacitors are covering a small share of the market. But still, there is a large interest in these processes, on these devices, because they could, in theory, fill really a gap between the two technology that could be interesting for many, many applications. Now, what we were basically discussing till now is the difference between supercapacitor and battery, how we can try to improve the performance of supercapacitors, the possibility to hybridize these two devices into one device. So this, of course, is an interesting topic, but what we have to be also aware is that there has been a lot of work on the hybridization of supercapacitors, not in sense of internal hybridization, so not trying to couple material for lithium-ion battery and supercapacitors into one device, but to couple devices, so to couple together batteries and supercapacitors. There is a very interesting work that is more than 10 years old of Rüdiger Kotz that was analyzing this and basically was trying to also give some indication about the possibilities. And I found this work very, very interesting, and I will use him as example for the following slides. And basically, in this work, when we are talking about hybrid system, we are talking about two types of systems. So the internal hybrid, like the lithium-ion, and the external hybrid. And these external hybrids are basically consisting on two devices, a supercapacitor, lithium-ion battery, or batteries, which can be connected in serial. So in this case, we can use the terminology external serial hybrid, or in parallel. In this case, we can use external parallel hybrid. Both strategies have some advantage. What has been shown, and this is very important, is that when we are combining a supercapacitor with a battery, not only lithium-ion battery, also lead-acid batteries, The life of a battery and the operating temperature range can be enhanced by the supercapacitor, by the coupling with the supercapacitor. Why? Because basically the supercapacitors in this combination is doing the work that the battery doesn't like to do. So, for example, is supplying the energy during the short time. So basically is removing the battery over a stressful situation. It can basically reduce the thermal stress of the battery. And we know that battery, of course, are suffering by that, by the fact that they may be subject to thermal stress, and the supercapacitor can buffer. So what has been shown in the past is that there is actually an advantage of coupling supercapacitor and batteries. But from the application point of view, in this year I was talking many times about this with many different companies. This coupling is actually seen as a positive, but often is not applied. Why? Because it becomes a matter of space and cost. Because of course, if we are coupling them, we have to buy two devices instead of one. This is increasing the cost, but what is also increasing is the space that we needed to put both of them. And we know, for example, that in automotive industry, every centimeter is precious. And so many car manufacturers, for example, were not going for this application because even if it was convenient and effective, it was too expensive and was not seen as a work to be done. So this is actually, I think, one of the points that in the future will be important really to discuss for the hybridization of supercapacitor to the technology, because often this type of hybridization, even if it's seen to be very positive, is not utilized for this reason, so for the cost and the space that is requiring. Nevertheless, there are some applications, like for example, the hybridization of supercap and battery in PV system, where this could be interesting. So, for example, there is a lot of work, of course, on the standalone PV power system, which are connected with energy storage. These are very important for example, off-grid rural electrification, and they have been widely used. What has been shown is that typically in this system, in many parts, they have been used in the past lead-acid battery. And the life of the lead-acid battery was often not high enough to basically be convenient, fully convenient. So this system were in a sense limited by the life of the lead-acid battery. What has been shown is that if a lead-acid battery could be coupled with a supercapacitors, and if we have a storage, maybe we have enough space to do this, then the life of the battery and then the possibility to use this system for longer time can become real. So this kind of application probably could be one of the future of the hybridization of supercapacitors. And this is something that is currently investigate and to try to see which are really the advantages associated to it. Now, coming to the end of this presentation, what I would like to give is some message. So the first one is that when we are considering this hybridization, the coupling is, of course, interesting and can be very, very advantageous, but is not as trivial as one can think about, because there is a lot of work that has to be done really to match the two systems and to match them in a way that both of them can benefit of this. So that the supercapacitor, for example, can increase the battery to a level high enough to justify the investments that we are doing. Or, for example, to try to minimize as much as we can the space that we need for this hybridization so that it can be implemented in different type of application that nowadays, simply because there is no space, are not available. So this is a very important aspect for the future that needed to be done. And here not only chemists, but also engineering, material science really needed to try to work together to reach this. And well, to conclude and to have an outlook of this work, what I hope I was able to show to you today is that supercapacitors are actually a real system, in the field of energy storage. You can buy them, you can use them, and there are many applications in which they are actually already implemented. This system have a very high power and an extraordinary cycle life. Their market is growing, is increasing, And they are very, very well suited for many applications, including, as we just saw, the hybridization with batteries. So supercapacitors are there, are already used, and there is a number of applications in which they can be used. Nevertheless, this technology is facing many challenges. One is the increase of the energy. So to be really competitive, the energy density of these devices should be increased between to 50-20 watt-hour per kilo. We should try to reduce the energy cost to at least less than 33,000 euro per kilowatt watt-hour per kilo, and keep the energy while keeping the power and the cycle life that we have currently. If this improvement will be realized, what is very important is that what is very interesting to notice is that the supercapacitors could really be used in many applications which nowadays are not used. For example, electric vehicle or other type of application. And would then this application basically realize it to the cost of the high power battery. So basically, they could replace, at least partially, some of the applications in which high power batteries, lithium high power batteries. And this is actually the big challenge that our community, so the community of working supercapacitors, is facing together with the industry. And with that, I'm at the end of the presentation. So I would like to acknowledge the funding agency that were supporting the work of our group in the last years. German, European. And what I would like to have as a last slide, in the case you are interested in the activity in supercapacitors, is to give you some idea about projects, some projects that are dealing with it. One is, of course, StoRIES, where supercapacitors are used in terms of hybridization, like the last part of the talk that I was just giving. There are some European projects, like the music project, dedicated to hybrid systems, so metal ion capacitors, project dedicated to novel double layers electrochemical capacitor like the green cap. And then for those that are interested on having maybe a PhD dedicated to this system, we are just starting a European project, a Marie Curie action project, so a training project in supercapacitor, which is called NRCap. So thank you very much for your attention, and I'm very happy to answer any question if they will be.
As compared to battery, which has enough energy stored to meet the demand, as it discharges after a long time, whereas supercapacitor discharges in a very short time, then how can a supercapacitor meet the purpose of application?
The question was maybe read 3:30, so maybe in the middle of the presentation. I don't know if I was answering later on. The question is which kind of application we are talking about. As we said, it's not just a matter of energy; it's a matter of how we are using the energy. So, for example, if you are misusing a battery. And when I'm talking about misuse, I'm talking about we are charging this battery in condition which the battery is not really suited for. The cycle life of this battery becomes shorter. And then, for example, what we need to do is to change the battery much more often than a supercap. This is, for example, a good reason to utilize in certain applications supercapacitors instead of battery. Of course, if we need a larger amount of energy, then it's becoming more complicated because the supercapacitor doesn't have maybe the energy that is required. But as long as the energy is enough, the cycle life may become a very good argument to use supercapacitors instead of batteries. I see that there is a question about the self-discharge. This is a good point. I was not mentioning this, but you are right. So the self-discharge of the supercapacitors is higher than the one of the battery due to the mechanism of storage. Because basically, what I was showing before is that when you are charging a supercap, you are polarizing electrode, and then you are, in a sense, forcing the ions to move close to this electrode. This is, from the energetical point of view, something that the system doesn't like to do. We are forcing the system to do something, and as soon as we are stopping to apply, for example, a potential, the system wants to come to an energy state which is lower, which is more favorable. In the battery, this is not happening because basically you are forcing electrochemically something to happen. So you are making a chemical reaction, and as long as the chemical reaction can proceed, then this system is stable then. And this is why the supercapacitors are having higher self-discharge. Nevertheless, about this point, maybe if another aspect is interesting, is that it's true, but for many application, companies are basically making some work where this self-discharge is not a problem. It can be for a shelf life. So if you leave a supercap for a long time without using, it can be a problem. But in many applications, this, for example, companies doesn't see this as one of the main problems for implementing these systems. The cycle life may become a very good argument to use supercapacitors instead of batteries. I see that there is a question about the self-discharge. This is a good point. I was not mentioning this, but you are right. So the self-discharge of the supercapacitors is higher than the one of the battery due to the mechanism of storage. Because basically, what I was showing before is that when you are charging a supercap, you are polarizing electrode, and then you are, in a sense, forcing ions to move close to this electrode. This is, from the energetical point of view, something that the system doesn't like to do. We are forcing the system to do something, and as soon as we are stopping to apply, for example, a potential, the system wants to come to an energy state which is lower, which is more favorable. In the battery, this is not happening because basically you are forcing electrochemically something to happen. So you are making a chemical reaction, and as long as the chemical reaction can proceed, then this system is stable then. And this is why the supercapacitors are having higher self-discharge. Nevertheless, about this point, maybe if another aspect is interesting, is that it's true, but for many application, companies are basically making some work where this self-discharge is not a problem. It can be for a shelf life. So if you leave a supercap for a long time without using, it can be a problem. But in many applications, this, for example, companies doesn't see this as one of the main problems for implementing these systems. I don't know if the slide is in the StoRIES website, because maybe that we have to ask Adeola how then will be managed this. I can share my presentations, no problem. I guess it will be recorded also. So yeah, as I said, for SAD, there are companies in Japan, for example, JSR Micro, which is working these lithium hybrid supercapacitors, and company in Norway, Beyonder, which is also working. I don't know if Beyonder has really commercial system, but JSR Micro, yes. So you can buy them. They are systems that can be both like any battery or supercapacitors. So in commercial system, SAD was writing. So I go before with SAD and then with Marcus. Which type of material are using apart from carbon material? I mentioned before, in commercial system, carbon are basically having are using in the large majority. There are attempts to use Mexine, a lot of effort, maybe some prototype, but industrial level, as far as I know, only carbon are used right now. in the future, it's not excluded that different type of material will be used, like MXene or graphene. For the electrolyte, there is a trend of trying to change the salt, so moving from the salt that is currently used to salt with different type of cation, because this is also a system that makes it is quite convenient for the implementation. Now, Sad was talking about lithium hybrid. So in lithium hybrid, if you are lithium-ion capacitor, graphite is the anodic material, and activated carbon, the activated carbon which is used for supercapacitor, is the positive electrode. As electrolyte, the commercial available electrolyte of lithium-ion battery is what people are using in these systems. I hope that I answered to your question, Sad. And Marcos was asking me the maximum number of cells to be serial connected. What is the technological limitation right now? I have to admit, I don't know. I'm not. In our cases, we were always studying prototyping, but we never been involved. So I have to admit, I cannot give you really a precise answer to this. I'm sorry. I mean, sorry, you are now talking about I mean, if you go to the website, maybe just to give you some indication, you can see the capacitance of the cell that the producer are offering. But I don't know how many of these cells are really then inside. This is sometimes not fully disclosed, or at least I was not aware of this information. Okay. Marini Giacomo was asking, which is the voltage windows in which the supercap works. We spoke about the maximum voltage, which is the minimum. Normally they discharge till the half, but you can also go to fully discharge. This is not a problem for a supercap. So depending of the application that you have, you can decide what is the potential which you want to discharge the systems. So this is actually one of the advantages of supercap, that you can fully discharge them and you don't have any problem to recharge them. So this is really then depending on the application that you are looking for, Giacomo. This is a good question. Normally you take the ESR, so the basically the ohmic drop that you are having while you are discharging. So you take the half of the ohmic drop and use this as a resistance for the calculation of the power. But depend nevertheless if you are calculating the maximum power of the average, sorry, the maximum energy of the average energy. You can also calculate the power out of the average energy, and you can use other type of system formula to calculate this. For the Nyquist plot, depend. You can take the depend on which system you have and if it's acid or not. So normally you take the first point then. The intercept with the real part of the impedance. No, I think it is. I think, Stefano, that US, the EU is not is still competitive in this technology. Actually, there are a lot of I mean, there are many companies, but I think that the gap is a bit different than in the lithium-ion battery. This is at least the feeling that I got in this year. So there is an open competition. If someone will come with a very good system, can become the leader of the technology. Then the problem will be if the market will increase enormously for the cost. But so far, I think that they are very, very competitive to the company. So there is not really a clear dominating, let's say, continent on this. Yeah, I think that it can be helpful. It's good for us. Yeah. Thank you for inviting me. So I guess that we are done. So I wish you all a nice evening, and thanks for participating to this lecture.